Delaware Tech, Chemistry 100, Chemistry 110, Unit 1 continued, density. So the definition of density is the amount of mass of an object divided by its volume. Or another way to say that is how massive the object is. We sometimes say heavy, but we really mean how much mass, not how much weight, an object has compared to its size. So it's the mass per size, the mass per volume. And density is a quantity that is independent of the amount of that material. Because if you have a large object, you have more mass for a larger volume. And if you have a small piece of that material, you have a small mass for that small volume. But the ratio of those two remains constant. Therefore, density is independent of how much material you have of that same material. So it's the ratio of mass to volume, and we abbreviated D. More properly, it's abbreviated with the Greek letter rho if you're taking a physics course, but here we're going to abbreviate it with a capital D. So D equals mass, M, and it's typically in grams, divided by volume, V, which is typically in units of milliliters. So our density unit is frequently grams per milliliter, but remember milliliters are the same as centimeters cubed or cc's. So grams per mil, grams per cc, grams per centimeter cubed are identical units. And in fact, they're also equal to the ratio of kilograms per liter, because kilogram is 1,000 times a gram and liter is 1,000 times per milliliter. Therefore, the ratio remains the same. So kilogram per liter is also the same ratio as grams per milliliter. Now there's another unit which is not quite the same. This is kilograms per meter cubed, and meter cubed is 1,000 times bigger than liter. So we use this unit for densities of objects that have very, very low density normally, and this would include gases. So here's an example of a fairly simplified problem. What is the density of an object with a mass of 54.2 grams and a volume of 31.7 milliliters? Now, if you look at the triangle right above, the triangle lets you it's a mnemonic for remembering the formula. What this shows is that M is equal to D times V. In other words, the mass is equal to the density times the volume, or you could say that the mass divided by the volume, so if you're looking on the left side of this triangle, the mass divided by the density is equal to the volume, and if you look on the right side of the triangle, the mass divided by the volume is equal to the density, and this is the original equation that we had. So we have an equation, we have a problem here where you're given the mass and you're given the volume, and you were asked for the density. So we can revert back to our original formula that density is merely mass divided by volume. So doing that problem, we take the mass in grams, divide it by the volume in milliliters, and we get this number 1.7098 grams per milliliter. Now remember, the amount of grams, 54.2, is 3 significant digits, and the volume, 31.7 mils, is also 3 significant digits. And of course, if we're looking for the lower of the two, well, they're actually the same number. So our answer should also be in 3 significant digits. Therefore, we round our final answer to 1.71 grams per mil. So let's talk about the ranges of densities. There are high density materials like the heavy metals. And while we haven't gone over the symbols of the various elements on the periodic table yet, I'm going to tell you Au is gold, W is tungsten, and the reason why it's W is because the Germans named tungsten wolfram, so it's W. Pt is platinum, Ir is a metal called iridium, and Os is a metal called osmium. And in fact, iridium and osmium are the 2 densest metals known to man. The range of these densities is between 19 and 23 grams per mil, and this is very high. Remember, this is how many grams are in a single milliliter. So that, comparing this to, say, water is our standard set at 1 gram per milliliter. So water, if you can imagine a small box that's 1 centimeter by 1 centimeter by 1 centimeter, a very small box, that if we mass that out with water, we would get 1 gram. But if we took the mass of that with these heavy metals, we would get about 20 grams. So these metals are 20 times denser than water because it has 20 times the mass for the exact same volume. On the other hand, if we look at gases like air, which is a mixture of gases, air is a homogeneous mixture. In other words, it's a well-mixed mixture of nitrogen gas, oxygen gas, a little bit of argon, trace amounts of CO2, trace amounts of water vapor, and a lot of other trace gases. This has a very low density, and you look to see the density in the same unit, grams per mil. You can see that compared to water, which is 1 gram per mil, air has a density that's almost 1,000th of that density, 0.00129 grams per mil. So we frequently use the other unit that I mentioned, kilograms per meter cubed, because that unit is 1,000 times smaller, and therefore we can use a number that is 1,000 times bigger. So we would say the density of air is 1.29 kilograms per meter cubed. Now, lower density objects tend to float on higher density liquids. Ice is slightly less dense than water, liquid water, and therefore ice floats. Mercury is the only metal that is liquid. There are actually 2 elements in the periodic table that are liquid at room temperature, mercury and bromine, but mercury is an actual metal, and mercury is a liquid metal at room temperature. And as it turns out, it dissolves most metals, but there are 3 metals that don't dissolve in mercury: iron, platinum, and tungsten. Iron, the symbol is Fe. That's because the ancient word for iron was ferrum in the time of the ancient Romans 2,000 years ago. Platinum, Pt, that makes sense. And tungsten, as I mentioned already, is W. So the question is, which one of these will float? Well, the question is really asking which one of these has a lower density than the mercury. And mercury is quite dense, about 13.5 grams per mil. So it's 13.5 times denser than water. It's very heavy for the same amount of water. So which ones will float? Well, here are the densities of iron, platinum, and tungsten. And you can see that one of these numbers is less than mercury, iron. So iron, bits of iron, would actually float on the mercury. However, tungsten and platinum, which have considerably higher densities than the mercury, these in fact will sink. As I mentioned already, ice is actually less dense than water, and this is very rare. The vast majority of solids are more dense than the corresponding liquid of that substance. In fact, water is one of the rare substances where the solid is actually less dense than the liquid. This is very unusual, and that is a result of the molecular structure of ice crystals, which we may touch on in another unit. Most wood is less dense than water, so most wood floats. Lignum vitae is a wood that's so dense its density is greater than 1, and therefore it actually sinks in water, but that's rare. Most rocks, as you obviously know, are denser than water and will sink. However, there are a couple rocks, including pumice stone, which you may have heard of for scrubbing your hands with in things like lava soap. Pumice stone is filled with air pockets, and as a result, the overall density of pumice is actually slightly less than water, and therefore pumice stone will actually float. But again, that's very rare. Helium is a gas that is typically much less dense than the air around it. So they're both very low density, but helium is even lower density, and therefore helium floats. And we know that because helium balloons will float up into the sky if we let go of them. A ship on the ocean is less dense than water. Now, this may not make sense. What's a ship made out of? Well, most ships are made out of solid steel or aluminum, which are metals which we know will sink in water. So why in the world would a ship, an ocean liner, an aircraft carrier, large ships that are filled with heavy metal in them, why would they be less dense than water? Well, remember, ships are not made of solid metal. They have rooms in them. They have compartments in them that are filled with air or possibly other gases. and the average density of the entire ship, including all the air pockets and the rooms and the compartments and maybe other things that are stored in the ship, make the ship on average have a lower density than water, and therefore they float. So here are 4 problems that involve density. Remember, density calculations are based on mass and volume. So some of these equations have mass and volume, some of them have density and mass, some of them have volume and things to calculate volume and the mass, and you are to follow the calculations. Now, if we look at the first problem here, what is the mass of an object with a density of 5.2 grams per mil and a volume of 52 mils? So what we have to remember here is this. We start with our original formula, and I'm going to just write it right here, that density equals mass divided by volume. But we don't want density, we want the mass. So we have to solve for this. So we can use the old methods that we used in elementary school, which is to multiply both sides by v, and the v's will cancel over here, and we'll end up with an equation that says mass is equal to density times volume. Well, we know the density and we know the volume. We merely multiply them together, and notice the volume unit in both the density unit and the volume itself, they're the same unit, so they will cancel. And as a result, and I'm going to erase these notes because it's written here on the screen, we start with the density, we turn it into the correct form, so we've isolated the mass in this formula. In other words, we've set the mass separate from the other variables, and then we plug in the numbers. And I didn't put in the unit for 5.2, I should have, but you would see that the volume cancels volume, and the only unit left would be grams. It would be 270.4 grams. However, notice that we have 2 sig figs here and 2 sig figs here, so our answer should have 2 sig figs in it as well, and therefore we would round it to 270 grams, which has our 2 significant figures. If we look at the next problem, we have an object with a mass of 3.2 grams, so we're given the mass, and a density of 1.06 grams per centimeter cubed. Remember, centimeter cube is the same thing as mils. What is its volume? So now we're being asked for the volume. So we have the density equals mass over volume, our original equation, and now we're solving for volume. So we have to rearrange this. Now, you might say, well, how did you go right from there to there? Well, we can cross multiply. We can move the v over here like we did before and have d times v equals m, just like we did in the first example. And then we can divide both sides by d this time. So d over here and d over here, and the d's will cancel, and we're left with this volume equals mass over density. Now, once we have the formula, now we can plug in the numbers, and you'll notice there's a grams here and there's a grams here, so those will cancel, and all we'll be left with is cubic centimeters, which is a unit of volume. We plug in the numbers, and we get that the answer is 3.0189 centimeters cubed, or 3.0189 milliliters. It's the same thing. And therefore, we now have to find how many sig figs there are. The mass has 2 sig figs. Our density has 3, so our answer must only have 2 sig figs, so we round this to 3.0 centimeters cubed, or we could say 3.0 milliliters. The next problem says, what is the density, so now you're being asked for a density, of a cube with a side that is 6.2 centimeters and a mass of 32 grams. Well, remember what a cube is. A cube is a 3-dimensional square, so all the sides are equal, so that's 6.2 centimeters, and the height is 6.2 centimeters, and the width is 6.2 centimeters, and the volume of a cube is just equal to the length of the side cubed. That's why we call it a cube, actually. And we plug that in, so it's 6.2 centimeters cubed, and then we cube everything. So we cube both the number and the unit. So the unit will be centimeters cubed in the end, and the number will be 6.2 to the 3rd power. Now I'm going to delete this because I believe this is all here on the screen anyway. So first you can calculate the volume. Now, normally we would round this if this was our final answer, but I'm going to tell you something that you're going to hear over and over again. Never round early. In other words, if you're not done with your final calculation, don't round the number too soon. Leave it with extra digits. Your calculator will say, sometimes even more digits. As long as you have many more digits than you will need in the end, you'll be fine. A good rule of thumb is that you have to have at least one more digit than what you need in the end. I tend to do 2 just to be on the safe side. So we now have our volume and we know our mass, so we just plug it into our equation and we get this value here. But we know that our original number had 2 sig figs here and 2 sig figs here, so we need to round our answer to 2 sig figs. And the answer is 0.13 grams per centimeter cubed, or 0.13 grams per mil. And this last question is actually very typical of what you'd see on an exam. A graduated cylinder has 52.1 milliliters of water in it. Now, I want to point out why we even say this. So a graduated cylinder is a cylinder in the lab. It usually has a base on it so that it can sit there. And graduated means that it has on it markings that are very specific and very tight on there that give you very accurate, precise measures of the volume. And that's what makes it graduated. The word graduated means stepped, as in grades, as in going to school, grades. It has the same root. So a graduated cylinder is a cylinder you can use to measure volume relatively accurately. And they're telling you that initially it has a volume here that reads 52.1 mils. Now, why did they even tell you that? Well, it then says when an irregular object, in other words, something that isn't this perfect cube that we just talked about here, that was involved in this question, it's some other weird shape. Well, you can't measure it and determine what the volume is. So how do we measure the volume of an object like that? Well, you put it in a liquid like water that it doesn't dissolve in. You literally just drop this chunk of whatever substance this is, and the water will raise up to some new volume. And the new volume here, if you read further, it says the object with a mass of 72 grams. So we know the mass is 72 grams. The water level rises to 73.9 mils. Well, if we know that this is 73.9 mils, once we added that little chunk of irregular object, we know the volume of the irregular object is a difference between these numbers. So I'm going to erase these notes because I believe this is all in here. So the volume is merely the final volume of the water minus the initial volume of the water. That's how large the object must have been, 21.7 milliliters. And we know its mass, so calculating the density is very easy once we have that volume. We just divide like we've always done. We get 3.30275 grams per mil. And because we have numbers that have 3 sig figs, 2 sig figs, 3 sig figs, our answer must be in 2 sig figs. And therefore we round this answer to 3.3 grams per mil. So the last concept we want to talk about here is specific gravity. And specific gravity is closely related to density. Specific gravity basically means it's the ratio of the density of the object to the density of water. Well, remember, the density of water is 1 gram per mil. And if we're using grams per mil, figuring out the specific gravity is incredibly easy. Remember the density of gold, for instance. Gold is Au. That's because the ancient name for gold was aurum. The density for gold is 19.3 grams per mil. Well, the ratio of this number to this number, if we're looking at the same units, is 19.3. It's very easy. So the specific gravity of gold is merely 19.3. So as long as you are using the grams per mil unit, the specific gravity, I'm sorry, did I say specific density? I meant to say specific gravity. Specific gravity is simply the density without the grams per mil unit. And it becomes quite simple. So I'm going to erase this. So the density of water, as I said, is 1 gram per mil. If we use grams per mil units, the specific gravity is just that number without the unit. So specific gravity has no unit. So as long as you figure out what the density is in grams per mil, that same number without the unit is just the specific gravity. So what's the mass of an object with a specific gravity of 4.78? Well, if it has a specific gravity of 4.78, that means it has a density of 4.78 grams per mil. And then you're given the volume is 60.0 mils. And you know that mass is equal to density times volume. Well, when you plug those numbers in, and I'm going to delete this because, again, it's on the screen, you merely plug it in. You get the mass is 286.8 grams. This number has 3 sig figs. This has 3 sig figs. So this number has to have 3 sig figs. So you're going to keep these and use that to round up the 6. And therefore, our answer is 287 grams.